Okay. Thanks for coming. It's good to be back here in Urbana. So I'm going to talk about the geometry of maximal SO2 comma and surface group representations. So everything I'll say is based on joint work with Nicolas Tholozan and Jérémy Toulisse, two French dudes. So start with some motivation and background and stuff, and then I'll talk about what I'll call a uniformization theorem. And then in the end, I'll talk about some geometry or geometric structures. Okay, so S is going to be this closed surface, and its genus is going to be at least 2 for the rest of the talk. So this will be one of, I guess, those 2 pictures, Chris. And gamma is going to be its fundamental group. Okay, in general, G is going to be some Lie group. And it's going to be a nice Lie group. A lot of times it'll be this Lie group. It'll be simple and real and stuff like this. So the main object that I like to think about is what I'll call the character variety. So what is this? I'll let it look at the set of all group homomorphisms from my discrete group, fundamental group of the surface, into my Lie group G, and I'll consider them up to conjugation. So I'll take a double quotient. So I act here by G on a homomorphism by conjugating the image. Okay, so this is the character variety. It has this nice action of the outer automorphisms of the fundamental group, which I'll think of as an action of the mapping class group of the surface. Okay, so studying a mapping class group action on this thing is something, well, lots of people care about. Okay, so what is the kind of main motivating example? So recall, I'm going to define the set of Fuchsian representations to be a set of group homomorphisms into SO21 that have discrete image and are injective, so discrete and faithful. Now I'm going to quotient by conjugation again. So in particular, there's a subset of the character variety where I put G SO0, 2, 1. Because 0 means this connected group, connected component of the identity. And what's important here is that this thing is the isometry group of the hyperbolic plane that preserves orientation. So if I take the hyperbolic plane and I quotient by such a thing, I'll get my surface back, and the hyperbolic metric will descend. We've got a hyperbolic structure. And I'm running out of room below. And then there's this kind of important theorem that says for all Fuchsian representations, there exists a unique, unique would be, I'll just say exists because we're quotienting, diffeomorphism between the universal cover of my surface and the hyperbolic plane. So diffeomorphism. So this is, of course, the uniformization theorem. Okay, so and through all this stuff, we can actually get this Fuchsian representations can be identified with the Teichmuller space of the surface. And of course, the mapping class group acts here, and it acts properly discontinuously. Okay, and so one of the things I want to kind of stress before going on is that when G is a real group, this space doesn't have a natural complex structure. Not at all. When it's complex, it does. And so the set of Fuchsian representations isn't a complex manifold. And it's really through the uniformization theorem or its identification with Teichmuller space that you get this nice mapping class group invariant complex structure. Okay, so of course you can quotient by this action and you get mg. All right, great. So the two important things of this is this. Well, here's one important thing. And here's the other one, is that these representations are holonomies of geometric structures, in this case, hyperbolic structures. And so the goal is to generalize this to higher rank groups. So this is an example of a group of rank 1. And I'm not going to kind of motivate the generalization. I'm just going to appeal to authority and say that Francois Labourie says to look at what are called Anosov representations. So rho. Okay, and so I'm just going to tell you a bunch of features of Anosov representations, and we'll see that they generalize a lot of this picture. Okay, so this Anosov condition is, well, more or less equivalent to there existing a unique, what I'll call nice, boundary map, which goes from the Gromov boundary of your group into some flag variety. So this is rho equivariant, and this is P is a parabolic. So this is a compact homogeneous space, and it's like a generalized flag variety. Okay, so what are some properties of these things? Well, first one is the mapping class group acts on the set of Anosov representations properly discontinuously. Oh, I guess the zeroth thing, which I'll put second, is that Anosov is the same thing as being convex cocompact if the rank of G is 1. Okay, so for PSL2C, this Anosov condition is looking at quasi-Fuchsian representations. And you should think of it as a good generalization of convex cocompactness to higher rank. And the third important property that I want to stress is, well, I guess I'll write their names the first time, is due to Guichard and Wienhard. They'd say, how do I want to say it? If rho is Anosov, say P Anosov, because it's labeled by this choice of parabolic, there exists an open domain, which I'll call omega rho, inside G mod P prime, on which rho of gamma acts properly discontinuously and cocompactly. Okay, i.e., Anosov representations are all holonomies of geometric structures. So maybe if I call it M rho is going to be this domain mod the group action is a G comma G mod P prime GX manifold with holonomy rho. So this last bit is going to be the geometry bit at the end, and it's, I think, a very interesting thing. It's a very great general theorem, but it gives no information on it's sort of more of an existence thing. There's no information on the topology of the domain and the topology of the quotient or anything. It just there exists these geometric objects. So during this talk, I'll talk about some special case into the group SO2N, and we'll see some instances of, well, we'll say something more about how this mapping class group acts, and we'll say something more about these geometric structures. Important thing to notice that missing from this thing, if the group is real, is a type of uniformization theorem that would maybe give such a set of representations a mapping class group invariant complex structure. Okay, so
do you know if the topology of these manifolds are at least independent of the representation? So if you have two different representations into the same group,
So they'll be homeomorphic, so it's like this Ehresmann-Thurston principle. So they'll be locally constant, the topology of these quotient manifolds. So if you have some good model representation, like some sort of inclusion of a Fuchsian representation, then you can do some work and then argue by continuity about the topology. But if you don't have any model representations, you don't get a point to start this game. Okay, so this is kind of the general picture. And so I want to say there's two important families of Anosov representations. There are these so-called Hitchin representations, so-called maximal representations. And let me just briefly recall, so if G is split, whatever that means, you should just think of it as PSONR or SON n plus 1 or whatever your other favorite split group is. There exists this unique, what I'll call irreducible embedding, what I'll call iota, from PSL2R or SO21 into my group G. Okay, if it's PSL2R, this is just and this is PSLNR, and this is PSL2R, it's just the unique n-dimensional irreducible representation. So the Hitchin component is the connected component that contains the image of the Fuchsian representations via this irreducible embedding. Okay, so when you're split, you have this unique kind of special embedding from the groups, and this induces a map onto character varieties. And this gives you a way to, say, deform the Fuchsian representations into this larger space. Okay, so that sounds like it's potentially interesting, deformations of holomorphic hyperbolic structures and stuff. But maybe you get everything, or maybe you can't deform at all, some sort of rigidity thing. So turns out that's not right. This is something that's super interesting. So let me tell you some facts. So Labourie and the Fock-Goncharov also, for general split things, say Hitchin representations are all in Anosov. Okay, so they're geometrically interesting. It's pretty windy. Okay. And then there's, it's called the Hitchin component. Hitchin, of course, before Labourie, but order of how I'm motivating him and not history, says that the Hitchin component shares a lot of properties with Teichmüller space. In particular, it's a vector space of dimension equal to the dimension of the group times the Euler characteristic of the surface. So for PSL2R, this is 3, this is 2G minus 2, it's 6G minus 6, and you get Teichmüller space. So in particular, the Hitchin component for SO23, this is an example of 2, n, so I thought I'd mention it, is the space of holomorphic quadratic differentials on some Riemann surface plus the space of holomorphic quartic differentials on that Riemann surface. So quadratic differentials just give you Teichmüller space, and this says there's a little more. There's the space of holomorphic quartic differentials. Important thing to note is this parameterization completely breaks the mapping class group symmetry, because I needed to choose this Riemann surface to get this description. But nevertheless, it's some vector space. Okay, so that's the motivation part. And now we'll start talking about the group SO2n and some maximal representations and from then on. But don't forget about the Hitchin component, because I've used some stuff about it later. I mean, don't forget about anything in the talk. I feel okay, so from now on, unless I say otherwise, G is this group SO2n plus 1. So, and this thing minus 1 will be important later. So, So you should think of this as a set of isometries or orientation of, well, Rn plus 3 cooked with some quadratic form, which is x1 squared plus x2 squared minus x3 squared minus xn plus 3 squared. Okay, so the maximal compact subgroup is SO2 cross SON plus 1. So this thing is not connected, so I should take the connected component of the identity, and that's what this little 0 means. And that's why this is the maximal compact. So in the set of Fuchsian representations, our main thing which we used to study everything was the hyperbolic plane. And how does that relate to the group? It's the Riemannian symmetric space of the group. So G modest maximal compact is the Riemannian symmetric space, which is one way to generalize what was happening with the hyperbolic plane for Fuchsian representations. And we'll think of this geometrically as a set of negative definite n plus 1 planes in R2n plus 1. Okay, so SO2n plus 1 acts in the space transitively, the stabilizer of an n plus 1 plane. That's negative definite, is you can rotate that plane, it's SOn plus 1, or you can rotate the orthogonal complement, which is the SO2. Okay. Great. So what does that mean? So if I have a point in this space, what is it is equivalent to giving me a splitting of my vector space as, well, ux plus vx, where this is R20 and this is R0n plus 1. Okay, so this would be a little important. Okay, so that's kind of some of the geometry the group will need. So given a representation, and remember G is SO2n. Well, what I'm saying right now doesn't matter, but okay, so I can build a flat vector bundle. So this is I'm just going to take my universal cover. I'll take the product with R2 comma n plus 1, and I'll quotient by, well, gamma rho of gamma. So this is a vector bundle over my surface. The fiber is exactly this R2n plus 1. So it actually has a quadratic form of signature 2n plus 1 on it. Now what I want to do is to choose a metric. So what's a metric? Well, a metric is just a reduction of structure to the maximal compact subgroup. So if I have just a vector bundle and I wanted to choose inner product on it, I would be reducing structure group to SON. Okay, but here I have a little more structure, so I will. It's exactly an equivariant map to this space. So choose an row equivariant map, any one for now, to the symmetric space. Okay, the symmetric space is contractible, so you can just, this is why metrics always exist. Okay, but what can I do with such a map? I wanted to write this a little lower. Okay. Well, there's this bundle over G mod K, which is G. So this is a principal K bundle. But remember, K is SO2 cross SON plus 1. So I want a quotient of that SON plus 1. This is a circle bundle. Okay, so what am I going to do? I'm going to pull back my circle bundle. And that gives me a circle bundle and universal cover. Everything's equivariant, so I'll descend to the quotient. So mod out by rho of gamma. And I take its degree. This is what I'll call tau of rho, and it's called the Toledo invariant of the representation rho. This is one way of defining it. Okay, so what is this metric? F rho is equivalent, this choice, and maybe I should have said it before defining this, to choosing a splitting of my flat vector bundle as U rho plus V rho, where this thing, there's a metric signature 2, 0, and this is 0, 0. So it's just a decomposition of the bundle like this. So the fact, this integer is bounded in absolute value by 2g minus 2. Okay, so it gives me a discrete invariant, and it satisfies this bound. Okay, well, hopefully now we can guess what the definition of a maximal representation is. So max are the set of representations such that tau of rho is 2g minus 2. Okay, so let's see it in an example. What's going on? So what happens when n is equal to 0? And rho is Fuchsian. Okay, well, when it's Fuchsian, I have this uniformization map, U rho, from the universal cover to the hyperbolic plane, which is the symmetric space. This is G mod K. Okay, G here is, well, this is SO12 or PSL2R. That's just the unit tangent bundle of the hyperbolic plane. So since it's a uniformization, I'll just pull back the unit tangent bundle. So what is the degree of U rho pull back the unit tangent bundle of H2 modded out by rho of gamma? Well, just the degree of the unit tangent bundle of the surface, which is 2g minus 2. Okay, so Fuchsian representations are maximal representations. Just the fact that you have this global diffeomorphism between your universal cover and the symmetric space, and the fact that the G, which is G mod SO1 in this case, is the unit tangent. Okay, so great. So Berger, Piazzi, and Labourie, and Wienhard tell you that maximal representations are also all Anosov. Okay, so they're all geometrically interesting in some sense. But studying their geometry is complicated because if n is bigger than 0, G mod K is, well, rank 2. In particular, it's not negatively curved. So it has two-dimensional flats. And lots of the things that make the hyperbolic plane nice is, well, one, it's negatively curved. And because of that, it has a nice boundary. So this being non-positively curved means this boundary is a little more complicated. It's stratified and stuff like this. But so instead of considering G mod K, we'll look at something else. Look at what I'll call H2 comma n, which is the pseudo-Riemannian hyperbolic space. So this is a homogeneous space for the group SO2 comma n plus 1. It's negatively curved, so constant has a metric G and G2n that has constant sectional curvature -1, but it's not Riemannian. It's pseudo-Riemannian. But it's a rank 1 symmetric space that is not Riemannian. So let me tell you how you should think of it. And this is my second picture. Okay, so H2n. You should think of as a set of lines, or in R, or we'll say it in lines which I'll think of as points in Rpn plus 2, such that when I restrict my quadratic form to L, it's strictly negative. Okay, so it's a set of negative definite lines in R2, n plus 1. Okay, so H2, 0 is a set of negative definite lines in R2, 1. Okay, so what does it look like? So in an affine chart of the projective space, it looks like a hyperbola, right? Because it's x1 squared plus x2 squared minus x3 squared minus xn plus 3 squared. And I want this to be negative. So here I'm drawing H21. It's the inside here. Okay, so what is the boundary? So it's negatively curved. It has this nice boundary. So how can a negative definite line degenerate? Well, negative definite, negative definite, negative definite, then I go to 0. And then I can do something else. But I have to go to 0 first. So the boundary is what I'll call G mod P1, a set of isotropic lines. So L such that Q restricted to L is identically 0. So it's also called this so-called Einstein universe. It's a really nice thing. It compactifies this space, and it's a conformal compactification with respect to this matrix. It has a signature 1n, etc. Great. So that's the space that we're going to consider. And now I can tell you, oh, and then I wanted to mention here that Berger, Yahtzee, and Wienhard say these are all Anosov, but if you remember, Anosov came with a choice of parabolic. Anosov with respect to P1. So there exist these boundary curves for maximal representations into G mod P1, which very conveniently is the boundary of the space that I'm about to, that I just told you about. Okay, so we're all set up to start talking about some theorems. Okay, so a theorem. Yeah, so see Tholozan and Toulisse. For each maximal representation, there exists a unique row equivariant space-like maximal embedding U row, oh, maybe I want to call it little u, U row from the universal cover of my surface into H2n. Okay, so what do the words in the theorem mean? Okay, so the first line is okay, row equivariant seems okay, right? The group acts here by deck transformations, and here this is a homogeneous space for SO2n plus 1, so SO2n plus 1 acts on it, you act by the representation. Space-like, maybe not, straightforward. What does space-like mean? Well, remember the image of the range, the target, is a pseudo-Riemannian manifold. But what can I do? I can pull back that pseudo-Riemannian metric and say what kind of object is that defined on my surface. So space-like, if this is Riemannian. Okay, so it means that the derivative, so the tangent space of H2n, tangent bundle decomposes into a direct sum u plus v, or this is a positive definite part and the negative definite part. So the derivative map here maps this onto u inside. Okay, and maximal is like a minimal surface, but you have pseudo-Riemannian things, so you can locally maximize the area. It's being space-like and conformal harmonic is the maximal condition. Okay, so that describes what the theorem says. So the picture is that if I fix my representation, I have one of these things here, this surface in this space. And one of the things we prove is that it extends continuously to the boundary, and it's exactly this Anosov boundary curve. So you can kind of fill in this Anosov boundary curve with this unique special surface. In some cases, it'll be totally geodesically embedded H2 inside, and that'll correspond to this representation factoring through SO2-1 in a Fuchs shape. But that doesn't always happen. Okay, so there's two consequences that I want to say. Maybe I won't actually get to the geometry. So two consequences. One is a proof of, an extension of Labourie's conjecture. And the other one is a description of the geometry, or in particular topology, of these quotient manifolds that I said from before. And so to do both of those things, we kind of use very explicitly the geometry of this map and how it use the negative curvature, the pseudo-Riemannian geometry stuff, and so on. Okay, so I need to talk about the first one before I talk about the second one, because it uses the things I would say in the first one. So if you're interested in the geometric structures, I can't just skip this and talk about that. So I apologize. Okay, so how does this work? So there's this. So I'll kind of tell you about some ideas of how you construct this surface. And of course, look at some large black boxes. So Corlett Theorem says for all representations, maybe just say, for each representation, here I don't need to be, this is G, this is a very general theorem, and for each X in the Teichmuller space of my surface, there exists a unique metric, or one of these unique equivariant maps to the symmetric space that is harmonic. Okay, so here I need to choose a Riemann surface, a Riemannian metric on this side and this side, but this one has one, to talk about harmonicity. I need to be able to measure things like take L2 norms of derivatives. But the harmonicity condition only depends on a conformal class of metrics in dimension 2. So that's why it's enough to pick a point in Teichmuller space. Great, so harmonic is really nice. Okay, but remember the kind of point of a lot of the parameterizations I talked about before is they broke the mapping class group symmetry. So this, again, requires fixing a point in Teichmuller space. but whenever you have a harmonic map, you can do something. Well, whenever you have a map, you can do this, but harmonic makes it very nice. I can pull back the metric here. And I'm on this Riemann surface, so I can take its 2-0 part. And the harmonicity condition tells me that this thing is holomorphic. And this is called the Hopf differential of the map. And what is it doing? It's measuring the failure for this map to be conformal. If it was a conformal map, I'd pull back the metric, and it would be type 1,1, dz tensor dz bar. So the 2,0 part would be 0. Okay, so now what does Labourie say? If rho is not any representation, but it's one of these special ones that are Anosov, then there exists, so this is like a for all, here's a for all there exists, x rho in Teichmuller space such that this h rho is a, we'll call it, is a conformal immersion. I.e., this thing is 0. Okay, and maybe it's branched, but more or less it's conformal immersion. So you can find a special Riemann surface structure where your harmonic map, which you knew existed, is better than harmonic, it's actually conformal. So the conjecture of Labourie says for each Hitchin representation, this special class of Anosov representations, there exists a unique x rho in the Teichmuller space with h rho conformal. In this case, it's actually not branched. Okay, so this is the conjecture. He proved existence. Sorry, Chris. It's that there exists a unique one of these things. And this is really nice if it's unique because it gives you a way of associating to each representation a kind of preferred Riemann surface structure in which to do these kind of jumps between Higgs bundle moduli spaces and character varieties. So the consequence, why it's so interesting and such an important conjecture, which is pretty wide open, it's known in some cases, the rank is 2 at least, is, well, if it's true, you get a description of the Hitching component as a vector bundle over Teichmuller space. So this is a vector bundle, and this is a mapping class group invariant or equivariant diffeomorphism. So it's a way of describing the mapping class group action on this space. And well, let's just do it for Hitchin component for SO23. And in this case, it's known to be true by Labourie. This, remember, is holomorphic quadratic differentials plus holomorphic quartic differentials. And this thing is H4, I'll call it. And the fibers are exactly the space of holomorphic quartic differentials. So it's a vector bundle of holomorphic quartic differentials over Teichmuller space. So this was quadratic differentials. This would be the cotangent bundle of Teichmuller space. In particular, it has a natural complex structure. That's mapping class group invariant. So the truth of this conjecture gives you a mapping class group invariant complex structure on the Hitchin. So it's very nice. Then the next game is to find Kähler metrics on this thing which restrict to like Bay-Peterson on the Teichmuller locus. Okay, so the next theorem. So T, T. For each maximal representation, and here G is any rank 2 Hermitian group, in particular SO2, comma, n plus 1, there exists a unique X row in Teichmuller space such that H row is a conformal embedding. Okay, so Labourie's conjecture, which is about Hitching components, holds more generally, if I assume the rank is 2 at least, for all maximal representations. And again, the reason this is kind of desirable is it gives you a projection map to Teichmuller space, and the fibers are not vector spaces anymore, but they're some scalar manifolds. Fx, scalar, and well, this is the start of trying to construct a mapping class group invariant complex structure on this thing, which you would like to maybe then study as complex geometry. Great. Okay, so maybe we'll say something about geometric structures. And okay, let me recollect. Oh, I erased my picture. Damn. Okay. So how does the proof of the first theorem work, which I erased also? Remember, there's this kind of unique special surface in this H2n. So here's how the idea of how these things work. So if I have a representation, I'm going to choose my Riemann surface. Remember, I have existence in general. So I'm going to choose one so in which H row is conformal. So I have a metric. I had my flat bundle before. And I said if I had a metric, I could rewrite that as that's the choice of a decomposition into a R20 bundle and an R0n plus 1 bundle. Okay, so what's nice about this big black box called Higgs bundles is it gives you a, so remember this thing also has a flat connection. It gives you a further decomposition of this thing. It looks like U plus W plus L, where L, so this is 0 n plus 1 signature. So L is a line bundle. This is all over my surface. Okay, so it's a line bundle, and in this thing it's negative definite. So a choice of a negative definite line subbundle here is exactly a map from an equivariant map from my universal cover into the space of negative definite lines. Okay, and so this decomposition of the flat bundle is exactly the way you prove existence of this nice map. And in this decomposition, the flat connection looks like, well, it has some metric pieces. And it has something here, and it has something here, and it has something here, which I'll call 1, and the important thing is it is nowhere vanishing. Okay. So now we'll talk a little bit about these geometric structures in the end. Let's see, what's 45. Okay. So recall. Okay, let me just recall that I have this map into this space G mod P1, which is a set of negative definite lines. And the Guichard and Wienhard construction gives you some domain inside G mod P2, which is a set of isotropic two planes, which is also called the photon space. Because you're supposed to think of them as projective lines in the Einstein universe whose norm is 0. So two-plane of isotropic two-plane is a line of isotropic lines. Okay, so a GX structure on some manifold M, well, it's a bunch of charts of my manifold, which take values in the space X, which is a homogeneous space for G, such that the transition functions are locally constant elements of G. Okay, so if this is PSL2R and this is the hyperbolic plane, this is describing hyperbolic structures. But it's equivalent to a pair of, well, there's a way of making these local charts global. You have a map from the universal cover into X, which I guess I'm assuming is simply connected right now. That's a local diffeomorphism. I guess I'm assuming my structures are smooth. And it's equivariant with respect to some representation, holonomy representation from the fundamental group of M into G. Okay, and so you can make a moduli space or deformation space of these GX structures, just like you did with Teichner space. Consider kind of marked GX structures up to isotopy. And then you have a map, of course, which is forgetting the developing map and just keeping the holonomy. And the Arison-Thurston principle says that this is a local homeomorphism. This is what Chris was kind of saying earlier. Okay, but I need to say one different way of thinking about this. Okay, so if rho is a representation of the fundamental group of M into G, what can I do? Well, I'm going to look at the kind of flat bundle over S with fiber my space X. Okay, and then I'm going to mod out here by pi 1 of n at rho. So this is a bundle over S, and the fiber is a fiber bundle. The fiber is this X. So a GX structure is equivalent to a this is an M. And so is this. Sorry. So I'm talking about a structure on M. It's equivalent to a section of this bundle. So that says at every point, I get a point in my homogeneous space. But you need this kind of local diffeomorphism property. So now you want to start parallel transporting the image of that section, and you want that to give you a local diffeomorphism between an open set here and an open set in X. So that condition is, say, that S is transverse to the flat structure. S is the section.
Oh, that's the section. Oh, I see.
Little s is transverse to the flat structure. Yeah. Okay, so I can at least tell you how the construction works. So I have my surface, and I have a set of, photons in my flat bundle. So this is this bundle with fiber, this photon space. So the fibers are photons in R2 n plus 1, and that's what I was calling G mod P2. But remember, I have this decomposition into as U rho plus V rho, W rho plus L rho. Okay, so, and this is negative definite, so this is a 2n thing. So I can look at photons in U rho plus W rho by themselves. And the fiber is exactly the photons in the image of my map to H2, n, at a point x, orthogonal complement. That U plus W is the orthogonal complement of L. So I pull back my bundle by this map pi. And since this is a subbundle of this, it has a tautological section. And so you compute that S transverse to the flat structure if and only if, well, this thing, when I wrote it over here, this part and this part, alpha is nowhere vanishing. So in the flat connection bit, you need these to be ones. That's the equivalent to this section defining a GX structure. Okay, and then you show the developing map maps bijectively onto the domain of discontinuity of Guichard and Wienhard. And so these are the geometric manifolds which arise as the quotients that Guichard-Wienhard construction gives you. So, thanks.
Questions? From this point of view, can you see anything about what happens if the representation is not maximal?
No. I mean, maximality is responsible for like everything here.
Yeah.
This one, well, the existence of other things, and yeah, no, it's yeah.
Maybe you could just repeat where was the rank 2 condition important?
Yeah, so the important thing was your rank 2, and you were able to find a rank 1 through the Riemannian symmetric space, which was also kind of a nice space that your group acted on. So this H2n is a rank 1 thing.
Ah, okay, yes.
And it has a nice boundary. If you're also important rank 2 was well, I don't know, kind of everything here. It's just like, so Labourie proved his conjecture in rank 2 for Hitchin things, and it just uses all the special features of what rank 2 is. Somehow you can reduce to something that's one less rank. That's rank 1, and then you can do stuff.
You have a candidate maybe for other Hermitian symmetric spaces of any rank, maybe related to Shilov boundary or something?
Yeah, so I mean, the Guichard-Wienhard construction says you are equivariant. You have this Anosov map of the Shilov boundary, but then the domain is in some completely different space. So the Shilov boundary is something that is, I don't think you can realize the Shilov boundary is the boundary of some symmetric space.
Well, it's a corner.
What?
Just a corner of infinity.
Yeah, exactly. But I mean, so here it's like, so that's an infinity of the symmetric space, of the Riemannian symmetric space. Here we're realizing the Shilov boundary of G mod K here as the boundary infinity of some other space, which was this.
But that's not the full boundary of infinity, right? Because you really would have a magnification of it. I mean, that's only a partial magnification.
Well, okay, this is drawn inside of an affine chart in RP n plus 2. It's really
yeah, but there's still sort of extra stuff that's not on this boundary on this codons here.
no. The boundary here is, just think of having a negative definite line and how you can degenerate it. It has to be 0.
Yeah, okay.
So this is the full boundary, but this is not drawing the whole thing because the space is compact.
All right.